Okay, so this is 11.3 Sine and Cosine Fourier Series. So just to get started again here on these definitions that I did on the last video, I just want to remind us of these. So if a function is even, when you plug in a negative, it basically disappears. It's an even function, which means, as I showed you last time, for example, is even. It's symmetrical, which means it's symmetrical about the y-axis. Then we have the negative gets pulled out. And what this means graphically, that it is symmetrical about the origin. And this is an example of an odd function. So just in general, if we integrate an odd function, we do get an even function. And if we integrate an even function, I mean, think about it, when you're taking the derivative or the integral, you're just increasing the power by 1. So it does switch from an odd to an even. But this is true for other odd and even functions like sine and cosine. You get an odd. So if we're actually, that's just in general, if we're actually integrating from minus p to p, well, I guess I can do a function. So we're doing a function that's odd. Then we get a function that's even. And then by fundamental theorem of Calc 1, we get f of p minus f of minus p, which is f of p, minus f of p. Because this is even, it disappears by my definition up there, which we get 0. And we can do the same thing, integrate minus p to p of a function that is even. Do it in general. We get f, the antiderivative, evaluated from minus p to p. We get odd, and we get f of p minus f of minus p. This negative goes in the front and makes a plus, 2 negatives. So you get double. And of course we get double because it's symmetrical around the y. And we could actually integrate it. We can just go from 0 to p and double it. If we wanted to, we can just do this half and double it, or the left half. So I want to recall the Fourier series that we did yesterday. So the Fourier series was that f of x, any function, can be written as a sum of sine and cosine. And we built formulas for a naught, an, and bn, where a naught is 1 over p, and the inner product of f and 1, which is 1 over p, and a n is 1 over p, the inner product of f and so we did an example of an odd function on the last video. You can see here, if f of x is odd, and we go and do our inner products of our constants, if f of x is odd, well then this will zero out. So that zero, the a naught is 0. If f of x is odd, we'll have an odd, and this is an even, and an odd times an even is odd. So b to the n will zero, a to the n will zero out. And the only one that doesn't zero out, yeah, that's supposed to be the sign. So an odd times an odd is an even. So this b and n is the only one that doesn't zero out. So our series expansion for f of x when f of x is odd is only this piece, where b to the n equals 1 over p. So similarly, the Fourier series representation. So now we're going to switch. So we can see if this is even, that doesn't zero out. If this is even times an even, that does not zero out. But if this is an even times an odd, we do get odd. The integral from minus p to p is 0. So that one does zero out. So the series expansion for an even function is the first two terms using a naught and a to the n. So as you noticed here, instead of going from minus p to p, I doubled it because definitely if f of x is even, I'm able to do that. If this is even and this is even, it can double from 0 to p. Just makes calculating it a little bit easier. So these are the half-range sines and the half-range cosine for odd and even expansions. So let's do an example. So since this function's only defined between 0 and 1, we don't know what it's defined on the left. So we can, depending on how it's defined to the left, depends on whether it's odd or even. So the first example, A, we're just going to assume if f is odd. If it's odd, you get the sine expansion. And for part B, we'll assume, assume f is even. So that's how we're going to work out these expansions. So we are going to use p is equal to 1 since f of x is defined and f is odd. This is what we get using the odd expansion. So f is odd, this is odd, so this is even, the product is even. So we could double it and go from 0 to p. F of x, we also have to break up this interval. It's 1 on the interval from 0 to 1/2. Oh yeah, and we are going to 1 here. I just said that. P is equal to 1. So it's f of x, yeah, times sine of n pi x. And we can break this up. So from 0 to half, the function's 1. From half to 1, it's 0. So from 0 to half, f of x is 1, sine of x is still there. This is 0. So b to the n, actually I'm going to distribute that negative in there. Just looks better. And so my f of x and if we wanted to, we could bring the 2 over pi out, but it's fine. So we can see here a naught, p is 1 still, and f of x is even. So yeah, it looks like we do need our x there. So f of x is 1 from 0 to 1/2. So I'm just opting not to do the second integral from 1/2 to 1 because the function's 0, so it doesn't need to be there. I put it in up there, but not this one. So my function, a naught was 1, so it's 1/2. So this and this is my an. That's part of my cosine expansion. And that's our example.